R is a relation, then R is the set of A, B, where A belongs to set A, B belongs to set B. Now, if we reverse the components, that means B, A, and we collect all those, then that set of B, A will form inverse relation of R. Here, 2 is connected with 4. That is represented by this. 2 is associated with 4, therefore, this is the arrow diagram. Already I have mentioned these two relations in the previous example. What is it? Null relation. A relation from set A to set B which does not contain any order pair element, of course element, that means in this case order pair satisfying the given condition. Actually, a restriction, a condition, a property, rule, law will be given for determining relation. If we find no order pair AB, where A belongs to set A and B belongs to set B, is not satisfying that restriction, then we get null relation. Then universal relation, already mentioned, that is relation from set A to set B. If we find that all the order pairs of A cross B is satisfying the restriction, given restriction, then we get the relation which is called universal relation. That means universal relation, if we denote that by the symbol R, that will be equal to A cross B. Already we have discussed examples in the previous example taken. Then we have inverse relation. Let R relation from set A to set B then its inverse relation denoted by R inverse, R to the power minus 1, but you must read inverse of relation R. is defined by R inverse is equal to set of BA ordered pair BA such that R is a relation, then R is the set of A, B, where A belongs to set A, B belongs to set B. Now, if we reverse the components, that means BA, and we collect all those, then that set of BA will form inverse relation of R. We take an example. AB, A has members 1, 2, B has members 5, 6, and a relation defined by A plus B equal to 7. Then what will be the inverse relation? First we find relation R. A plus B equal to 7. First we consider the first element 1 and we add with each of these. First will give 6 and the second one will give 7. Therefore 1, 6 is one order pair. Then we take 2 and add to each of 5, 6 and get 7 and 8, but the restriction is sum 7. Therefore it will be 2, 5. Thus the relation is the set of order pairs 1, 6 and 2, 5. Therefore its inverse will be just we reversed the components of each of the order pairs and get inverse relation R inverse is equal to order pair 6, 1 and 5, 2. Now for this domain is set of 1, 2 and range is set of 5, 6, and for the inverse domain of R inverse is 5, 6 and range is 1, 2. That means in this case domain of R inverse is the set P. This is set P and range of R inverse is set A. That means domain and ranges of R are just reversed. Now we discuss how how we represent a relation from set A to set B. One is roster form. Actually, we have discussed the examples earlier and represented the relation in roster form. Then there is another arrow diagram. To clarify that, we take example. Taken set A members are 1 to set B members are 4, 5 and the relation A to B defined by B equal to 2A. Then R will be equal to 2 times A is equal to 2, that is not member of set B. 2 times 2 equal to 4, that is member of B. Therefore, in this case the relation will be this is roster form. We have mentioned here all the ordered pairs separately. Then for arrow diagram, this is set A and here we are applying in diagrams actually. Then 4, 5, now the member is 2, 4 and we give this which indicates the relation R. Here 2 is connected with 4. That is represented by this. 2 is associated with 4. Therefore, this is the arrow diagram. Normally, we use these two representation, roster form and arrow diagram. We have taken one example and clarified that. Next, we move to binary relation. On a set. Binary relation or relation. Actually, here the order pair contains two components, that is why we call binary. Let A be a non-empty set, then a relation R having ordered pairs AB such that A is member of A, B is also member of A. That means first component, second component of the order pair both are members of the same set A. In this case, we call a relation on a set. That means here codomain is set A and the domain of relation R will be subset of set A. This is binary relation. We take example. To find R A to A such that I have taken set A that is equal to set of 1, 2, 3. Now we are going the relation on set A represented by this symbol also R from set A to set A such that A plus B will be equal to 4 where A, B both are members of set A. Then what will be the relation? One plus 3 that is equal to 4. Therefore, 1, 3 will be an element. Then 3, 1. Actually, first of all, we have to consider here the Cartesian product of A cross A. Then 1, 3, 3, 1. Both will be the order pairs. Both will be elements of A cross A. Therefore, 1, 3, 3, 1. Then 2, 2. Therefore, relation from set A to set A will be the set of the order pairs 1, 3, 3, 1 and 2. Now let me mention how many relations can be formed from set A to set B. Say RP relation from set A to set B where cardinal number of set A is equal to small p and cardinal number of set B is q. Now, how many relations can be formed? The answer is number of relations formed from A to B is 2 to the power pq. 2 to the power pq. How? Total number of ordered pairs, those can be formed for A cross B is P into Q. Therefore, total number of relations, those can be formed from set A to set B will be equal to 2 to the power number of order pairs of A cross B, that is 2 to the power pq. That will be the number of relations. Total number of relations you can mention is 2 to the power pq. Now, relations or binary relations on a set, generally we consider the relations where domain, range both will be subsets of set of reals. Relation are on set of reals. Generally we consider relations on set of reals. Let us take one example. Find R on set of reals. We take positive reals, not that we take set of naturals, that is also subset of set of reals such that x plus 3y is equal to 12. We are considering relation on set of reals. Since set of natural is subset of set of real, we are taking here the condition 2x plus 3y is equal to 12. Now we have to find the relation R. We solve this problem like this. First of all, we write 2x plus 3y equal to 12. Then express that in terms of now we form the table. Like this, keeping in mind that x, y both are positive integers. Now if we take one, 12 minus 2, that is 10, the result will not be integer, then 2, 3, 6, 12 minus 6, 6, 6, 6, then 0, then since x, y are natural numbers, therefore these are rejected. Therefore, in this case, the relation will have only order pair 3, 2. This will be the relation. Thus, we have discussed relation R on set of reals. Next, types of relations. course. What will be the types of relations on set A? Already we have mentioned non-relation, universal relation, then identity relation, number 4, reflexive relation, number 5, symmetric relation, number 6, transitive relation, transitive relation, then equivalence relation. Already we have mentioned non-relation, null relation, universal relation, then identity relation. We have to discuss these identity, reflexive, symmetric, and transitive and equivalence relation.